To finish up our discussion on Euclid's number theory, we're going to consider runs of natural numbers that are composite. Okay, so if we're looking for runs, in other words, consecutive strings or runs of numbers that are composite, for example, let's see, I'm looking for strings of numbers that are between two consecutive primes. So let's see, we could do 6, no, 7's a prime. We could do 8, 9, 10. That's a run of 3 composite numbers in a row. Let me go up to a higher number. Let's say after 13, I could start with 14. That's a composite. 15, 16. That's still only 3 in a row. Let's jump up to, let's see, prime number 23. 24, 25, 26, 27, 28, and then 29 is prime. So that would be 5 composite numbers in a row. Well, the theorem says that runs of composite numbers are arbitrarily long. So for example, if you said 1,000,000, at some point you can easily find 1,000,000 numbers in a row that are all composite. Or 1,000,000,000. You could find 1,000,000,000 numbers in a row that are all composite. And that's what we're going to prove here. So it is pretty fascinating to think. There are an infinite number of prime numbers. But there are, if you get large enough numbers, you can find arbitrarily long sequences of numbers that have no prime numbers in them. They're all composite. Okay, I've rambled on enough about this. Runs of composite numbers are arbitrarily long. Proof. Let's let k be a natural number and let n equal k factorial. And I'll go ahead and remind us what k factorial is. K factorial is k times k minus 1 times k minus 2 all the way down to 3, 2, 1. So it's the product of the first k natural numbers. So let k be a natural number and let n be k factorial. Okay? It follows that the k minus 1 consecutive integers starting with n plus 2, so n plus 2, n plus 3, n plus 4, and then we go all the way up to n plus k, are all composite. And we're going to take just a minute to show that, and we'll be done. So, for example, if you wanted 1,000,000 consecutive integers that are all composite, well, I would have to get k minus 1 means I would have to let k be 1,000,001 and let n be 1,000,001 factorial, which is a ginormous number. Okay, so let's just show that what I said here is true. Let's show that all of these numbers are composite. Well, notice n plus 2 is equal to, well, n is k factorial, so 1 times 2 times 3 times k plus 2, right? Well, we've got two terms here, this big thing and 2. Let's factor a 2 out of it. You would get 2 times, so this 2 is going to get canceled out in a sense, 1 times 3 times 4 times 5, all the way up to k plus 1. And I shouldn't have used this parentheses. All right, so convince yourself. I wrote it a little bit messy here, sorry about that. N plus 2 is k factorial plus 2, and 2 is a factor of this, and 2 is a factor of this because it's contained right there. I pull the 2 out, and in parentheses, I get 1, 3, 4, 5, 6, all the way up to k, plus 1. Let's take a look at n plus 3. Well, that's going to be 1 times 2 times 3 times 4, all the way up to times k, plus 3. Well, notice 3 appears in this, so I can factor a 3 out of both of these. 3 times 1 times 2 times, I have to skip 3, so 4 times 5, all the way up to k, plus 1. We did the same thing again. 3 was a factor of this, 3 was a factor of this, so I factored out a 3. So we've proven that n plus 2 is prime because 2 goes into it. It's an even number. N plus 3 has a factor of 3, so it's not prime either. Well, we could just keep going down all the way, kind of repeating that pattern, all the way down to n plus k. N plus k is equal to 1 times 2 times 3 times 4, all the way up to k plus 1. All right, so now I'm going to do this. I'm going to write this as, n plus k. It's plus k there. Sorry about that. So we took, this is n factorial plus k. Now I'm going to factor the k out. So pull out the k, because k goes into this. It's going to be 1 times 2 times 3 times 4 times ... and it's going to stop at k minus 1 plus 1. Okay, so you can see what the pattern is. We've got k minus 1 numbers here, starting from n plus 2 going to n plus k. And we've shown that every single one of them is composite because we factored out a number out of each of them. So none of them is prime. So that is the end of the proof.